And notice that that first one I've highlighted, that's just to keep me from wandering around. I went in advance and highlighted the ones that I want to talk about. And one thing you'll notice about these review documents is there's a good bit of repetition, approaching a problem from different angles. So what I'm going to do is with these highlighted ones, I'm going to cover topics without being redundant if possible. Okay, but yes. Yeah, sure. Did you miss getting any? Yes. Oh, yeah. Okay. So here, this is the these are the PowerPoints. These are the ones I want you to memorize. The same ones. Okay. And this is a review document. The key to the review document is in bright space. Okay. Yeah. Okay. But if you get stumped and you need to see how I worked it at least once, there's usually several ways to work a problem, but this is how I did it one time. That's number. These are the same numbers as on the review document. Okay. And then I've only got one of these left. One. This is chapter 2. Crossword puzzle. This is extra credit. But there should be a chapter 1 in bright space also. Okay. And then this is an extra credit periodic table. Right? Those are your instructions. There's where you fill it out. And then this one. When we get to we haven't named compound yet. Yes, we have. Yeah, we did chapter 2. Yeah. Okay. So so both of these extra credits are for exam 1. Okay. And they're nice. Did I give it to you? Yeah. That wasn't enough. Okay. So what I want to do when we get to a review day, I want to tackle any of the problems that you bring up first before I jump in here. This is just so that we'll definitely cover the topics, but if there's one problem in particular, even if it's not one of my highlighted ones, then let's jump on it and figure out where the problem is. And so if you don't bring me any problems that you've had with the review document, then I'll just go ahead and start. Okay. And at any time during this process, if I'm explaining one of these and it doesn't click, if it doesn't make sense, then stop and we'll figure it out. Okay. All right.
What would you give us with your, can you give us anything?
You'll notice in the review document, if you look on the back pages. See, on this one it starts on page 34. This is useful information. This these are your polyatomic ions. And they're periodic table. Anything that's in the review document and useful information will be on the exam too.
How many questions is there?
It varies.
A lot, but
Not as much as this.
okay.
A lot less than this. This is for drilling and mastering subject.
In those practice tests on bright space, do you have to take all those before you take the exam?
Oh no, you can have to do any of that if you don't want to.
Right.
No, that's a review. Those are reviews.
So that's not.
No, I don't see those grades. That's so you can run through them like a bright space exam, and then it'll grade it for you and show you which ones you got wrong. And you go back and focus on your weak spots.
The ones that say easy, moderate, difficult, you don't see those.
No, they're segregated like that just to give you an idea of whether the problem should be easy to solve, moderately easy, or difficult. Now the exam is going to be the paper exam. I don't think I brought it with me, but it looked just like that review document. So if you use the review document as if it were an exam, it'll give you practice with the format and the type of questions that you're likely to encounter. So it's not a complete shock when you walk in and try to take one of my tests. Of course, after the first couple, should get pretty comfortable with the way I ask questions and the format.
Which I've been thinking of that, is the word problems. And is this thing pine or pain?
Pine.
Pine, okay. I met with him Sunday and he tried to show me how to set it up. And he does it like, he talked about it being like a fence and he just goes through and times all the top and divide all the bottom straight across. You know what I'm talking about?
When you're doing a unit conversion? Yeah. Yeah.
But still, that's confusing on how he sets that up. That's the only issue.
Does he use parentheses or does he use lines and crosses? Yeah. That's okay. You can do it either way. I like parentheses, but that works okay. Parentheses would be like, there would be parentheses here, there'd be parentheses here.
Okay.
Right, that's nothing special. That's just a preferred format.
Yeah, so I'm a little bit.
Yeah, word problems are designed to confuse. Right? What they're trying to do is to see if you really know the subject. If you can pick out what you need from the word problem to solve it. If you can identify the question so that you can get the answer. And word problems typically have some blue smoke built in, right? Just to blow up in your face and confuse you. So you got to stay focused on what the question is and then go to the problem and say, information is here, or I have to go outside to get the information. Usually that means either a formula from useful information or the periodic table. But lots of times the word problem won't have everything in it that you need.
Some of the times too, it does, but it has too much and you have to minus or plus things. And add stuff together to get.
Yeah, if the word problem is asking a very complex question, then what you have to do is with time, develop the skill of breaking it down into smaller, manageable pieces. And solve this problem, this problem, this problem. Then you can put them all three together and get the answer. Hopefully we'll get into those types of problems here. Maybe not in this for this exam, but maybe in the future they become more complex. And that's why I do these reviews, so that you get a taste. Let's see. I think in this review, I've got them segregated by chapter. So I better put chapter 1 here and then number the problems. When we get to chapter 2, it's going to start renumbering all over again. Okay. Which of the following is an example of a quantitative observation? What do we mean by quantitative?
Measure.
There's invariably a number involved. A number and a unit with a quantitative observation. So, and the other possibility is qualitative, which is just a general observation without numbers. A piece of metal is longer than the piece of wood. That's qualitative because it doesn't tell you how long it is, just says one's longer than the other one. Solution 1 is much darker than solution 2. Similarly, that's qualitative. The liquid in beaker A is blue. We're still qualitative. We haven't introduced any numbers at all. The temperature of the liquid is 60 degrees Celsius. That's your quantitative. So 1 will be D. Generally observed behavior that can be formulated into a statement, sometimes mathematical in nature, is called. This is where we differentiate between a law and a theory. A law just says how. And a theory attempts to say why. So in this case, your observed behaviors are formulated into a statement. That's just a law. It makes no attempt to explain why this statement is true. And I think my examples I gave you were Newton's laws of motion. Do you remember this one? Force equals mass times acceleration. Did I use that in this class?
No.
Well, must have been a different class. But that's just a law. And we're going to encounter several laws. We get quite a few of them when we study gases. There's several laws of the gases. And then we follow up actually with the gas laws, and then we follow up with a theory that explains why those laws work. But to answer this question, it's D. It's a law, natural law in this case. And that brings up another point. When you're taking a multiple choice test, especially if you are calculating an answer and you're supposed to have a number with units of measure, and you have just certain choices to pick from. If there's not one in there that says two of the above, none of the above, and that kind of wonky stuff, if they're just straight answers, A through E, then pick the best one. Okay. All right, that was 2. I think I like these markers because they don't erase. Let me see if I can find a better one. Here we go. These expos, you got to use water to erase these things. But the ones I bought for myself, they work better. Okay, that was 2. And 5. Initially, there's going to be quite a bit of memorization because you got to learn the language before you can speak it. In this case, what do these prefixes mean? Well, we want to order these prefixes, these metric prefixes from smallest to largest. And I think the best approach to this one is to look at the answers and pick out the unique answers. Right? We've got a nano. We've got a milli, centi, and kilo. Milli, centi, kilo. Let's see if we have any other new let's see, centi, kilo. No, that's it. We just have the 4. Now we want to put them in order from smallest to largest. So which prefix represents the smallest multiplier? Nano, yeah. 10 to the minus 9. Milli? 10 to the minus 3. 1,000. Centi? 10 to the minus 2. And this is 10 to the 3rd. Times whatever base unit follows them. Okay, so if we put them in order, smallest one is this one. Actually, they're already in order. So I wrote them up there. So A is the answer. Because that's the one I was picking from. That erases a lot better. And let's see, we can get 6 and 7 on there. Okay, 8.1 kilograms contains this many grams. 8.1 kilograms. And we want to equate that with how many grams? We're just changing the units of measure. And if you're going to change the units of measure on a value with a unit, you need a conversion factor. Remember what all conversion factors have in common. Every conversion factor is equal to 1. That means if it's, say we remember a conversion factor. Let's see, 1 kilogram equals 10 to the third, 1,000 grams. Well, that won't work because that's in the numerator and that's in the numerator. We need to cancel the ones we don't want and leave us with the ones we do want. So what I've got to do is change my units, and these numbers will change also. Just flip it. So it's 10 to the third grams. 1,000 grams is 1 kilogram. Now they'll cancel. This is in the numerator. Remember, if you have something sitting there by itself, it's always over 1. So that's the numerator. This is the denominator. Those cancel. Get rid of the ones you don't want, leaves you with the one you do want. So now we have, actually, that's pretty easy. Let's see, what type of answer we got? Scientific notation. So this is going to be 8.1 times 10 to the third grams, which is B. Okay. So in the beginning, a lot of the problems are going to be simple, going to be easy like that. And as we progress, they'll become a little more and more difficult as you gain competence. 7. All right, what do we want to do next? Convert 0.3980 meters to what? Millimeters. Okay. You could probably eventually do this one in your head. But for now, we're going to use conversion factors. We want to get rid of meters on the bottom and leave us with millimeters. So how many millimeters in a meter? Well, if a millimeter is 1,000th of a meter, it takes 1,000 of them to make a meter, doesn't it? You can do it either way. You can say 1,000 millimeters makes a meter, or you can say 1 millimeter is 1,000th of a meter. That throw you a curve. Look at it this way. M. What does that mean? Well, milli means 1,000th of times a meter. I just substituted 10 to the minus 3 for what that means right there. So that's where this comes from. And if we had, say, 1 kilometer, kilo means 1,000 times. So that's 1 kilometer is 10 to the third meters. I just substituted what its equivalent is. 10 to the third, 1,000. Okay. All right, so let's get back to the problem. All right. So in this case, if 10 to the minus 3 in the denominator and we move it into the numerator, we just change the sign, right? And so this is going to be 10 to the third. 0.3980 times 10 to the third millimeters. But let's look at our answers. Okay. We wanted scientific notation. So that means we have to move the decimal over here. 3.980 times, what does that do to this one? Well, we stored up a small number. If you move the decimal to the right, the number gets bigger, so this one has to get smaller. Let's see which one that is. Oh, it's got a mix of scientific notation and standard notation. So what would this be in standard notation? 398, right? Because this is 100. So what's 100 times 3.9? It's 398. Nobody's fallen out of their chair yet, so I think it's safe to move. All right. Number 9, this is just definitions. What's the measure of resistance an object has to change in its state of motion? This refers to actually Newton's first law. An object at rest will remain at rest unless you push on it. That's mass. Mass is a measure of resistance to motion. All right. Let's see if we got what we can do here. As part of a calibration of a new, let's see, put this down here. I can read it from back there. As part of a calibration of a new laboratory balance, 1 gram mass is weighed with the following results. So we have a standard. Let's see, number 11. We have a standard that we know has this mass. And then we put it on the balance and we get 3 times we measure it. And each time we get 1.201 plus or minus 0.001. And then the second one we get 0.2, 2, and 1.200, I think. Yeah. Plus or minus 0.0. This is an expression of uncertainty. If you take statistics, then you'll be introduced to this stuff. But I want us to focus on these numbers right here. If we get these values, 3 measurements of that mass, what does that say about the accuracy? It's not accurate. We're heavy by 0.2 of a gram, which is about 20%. Right? That's a pretty big error. So it's not precise. Excuse me, it's not accurate. It's not accurate. But look at the spread. Right? They're within this margin of error of each one of them. So they are precise. They group fairly closely. So let's see. The balance is not accurate, but precise. C, precise, but inaccurate. See how we arrived at that conclusion? So if a technician had come to your lab and was standardizing your balance, he or she would have to make adjustments to it. They have the ability to make adjustments to your balance so that the next 3 that it weighs will be very close to that value. But this first series of weighings gives us an idea that our precision is pretty good, but the accuracy stinks. And we've got to correct for it. Right. Okay. Questions 12 through 13 refer here. All right. Let's see. We're looking at those 3 targets. Which of the following figures represents a result having high precision? That is, tight grouping. Well, I think 3 does definitely. And so does 2. Right? They're both. So 2 and 3 would be E. Okay. How about 13? Which of the following statements figures is correct? All right. So now we have to read each one of them. Figure 1 represents systematic error. All right. Systematic versus random error. Let's talk about that a minute. Types of error. Systematic versus random. Systematic error is the type of error
that we can identify how it got there. In other words, it's always wrong by a certain amount. So if a technician were analyzing a sample and they said had so much percent of gold in this ore, and they did the analysis 3 times, and this was a check sample. Right? Analytical labs always do this. They exchange check samples. They have an agreed upon value in the check sample, and then your lab runs it as an unknown, and then they submit their values and we compare them. So we know that this sample is supposed to have, say, 0.0089% gold, which is pretty low actually. But this is just for argument's sake. If you're a technician, the technician in your lab always comes up with something like 0092 or 0.0093, 0.092. It's right in that range. They're always high by a certain amount. Right? That's a systematic error. They're making the same error over and over again. Or it could be based upon the instrument that you're using. Could be an error. Systematic is identifiable error, and you can correct for it. Right? All we have to do is take those values once we know what the systematic error is and subtract 0.0003 from it. And we get close to this value. That's the good kind of error that we know where it's coming from. Random error, you don't have a clue where it's coming from. It could be anything. My last degree was in agriculture, and we'd have various types of experiments. We'd have a greenhouse, grow plants in the greenhouse, grow chamber, which is very controlled. And then we'd always have to have some out in the field. And it would usually take 3 to 5 years to get enough data so that you could average out the variables, because natural variables of climate and weather patterns mess with your experiment. Those are random errors that we can't control. So the only way to deal with random error is express what it is, right? And hope that over time and with large sample size, you can reduce the impact on your outcome so that you can actually draw conclusions from the data. Random error is the bad kind, but we always have to deal with it. And statisticians have given us tools to deal with random error. So let's go back to this problem and say, how does it fit with systematic error versus random error? As far as these targets go, systematic error is one where you get good precision, but it's not accurate. That's a systematic error and can be corrected. So if you were sighting in your scope for your rifle and you got number 2, you got Roman numeral 2, that's good, because you can correct for that. All right, you just dope the scope and bring them all back down on. So that's 2 is systematic error. 1 is random error, right? It's all over the place. So let's see, that would be figure 1 represents random error. Yes. And figure 2 represents systematic error. True. That's B. All right. Let's see, how about number 16? The amount of uncertainty in a measured quantity is determined by what? Let's think back to that referee sample that our technician was analyzing for gold. What contributes to the error? Well, there are really only 2 things. One is the skill of the technician, and the other is the accuracy of the instrumentation. That's the only 2 you have. It's only 2 possibilities. And that would be A, both the skill of the observer and the limitations of the measuring instrument. And you have to take both of those into account when you're trying to get a handle on uncertainty, on error. Okay, 17. A scientist obtains the number 4,500. $6,700. Okay. On a calculator. If this number actually has 4 significant figures, how do we express that number with only 4 significant figures? You have to decide, since you got zeros in there, which zeros are significant, right? These are not significant, not at all. These are bracketed by non-zero numbers, so yeah, they're significant. These trailing zeros are significant because we have that explicit decimal right there. So this number right now has 1, 2, 3, 4, 5, 6, 7, 8 significant figures. But that's what our calculator tells us. What we learn from the calculation itself is what the limitations are. And the limitations say we can only have 4 significant figures. So where do you start counting? You start right here, because those are not significant. 1, 2, 3, 4. So you look right here, and you look to the right, that's greater than 5, 0.04501. That would be 4 significant figures. And the answer would be E. Okay. Right, 17, 20, and 21. Express the number 0.0810. 0.0810 in scientific notation. All right, so what are the requirements for scientific notation? Coefficient must be between 1 and 10. And the coefficient expresses the same number of significant figures as the standard notation. So how many do we have here? We got 1, 2, 3 significant figures. So we're going to move the decimal here, 8.10. And we move to the right, storing up smaller powers of 10. We move twice to the right, -2. Remember when I said as the number gets bigger, power gets smaller. So if you move to the right to make the number bigger, then the power of 10 has to go negative. If this were a big number and you move the decimal to the left, the number got smaller, the coefficient got smaller. That means the power of 10 had to go positive. And this is D. D is the answer for that. Okay, express the number in common decimal form in standard notation. So we're going back the other direction. 6.49 times 10 to the -3. Okay, so we got 6, 4, 9. And we're moving 3 places to the left. So we go 1, 2, 3. But 0, 0, 6, 4, 9. And wait a minute. Yeah, oh, there it is. A. Okay. The only way you're going to get comfortable with this stuff is to do a lot of them. Practice, practice. Okay, 22. Express the number 2.37 times 10 to the 4th in common decimal. Okay. So for this one, we're multiplying by 10,000. We're moving to the right. If we're taking this large coefficient, the power of 10, then this number is going to get bigger. All right, so we're going to go 4 places to the right. 1, 2, 3, 4. Right? But I can't keep that decimal in there. Why? Because if I do, I'm saying 1, 2, 3, 4, 5 significant figures when this only has 3. So I've got to say 2, 3, 7, 0, 0, no decimal. That means we still only got 3 significant figures. Did I lose you?
Can we redo that?
Okay. If you look at it this way, what's 10 to the 4th? 10 to the 3rd is 1,000, 10 to the 4th is 10,000. So we say 10,000 times 2.37, then it should be 237. It should be about 23,000. Yeah, there we go. But we can't put a decimal down there because the coefficient says we only have 3 significant figures. So we got to leave the decimal out, and those zeros are not significant.
Do you keep the same amount of significant figures or the lowest amount in problem of significant figures? That's what you want your answer to be, the same amount.
Okay, if it's multiply, divide, yeah, the factor with the smallest, the number with the smallest number of significant figures dictates the answer. But with add, subtract, you line up the decimals. And the number of significant figures in an add, subtract operation could be different than either of or any of the additions. We'll probably get an example in here coming up. Yeah, that's the mistake a lot of students make. They apply multiply, divide to all operations. You know, just take the least number of significant figures but it won't work. If all of your operations are multiply, divide, you got a series of them, that's fine. It works great. But if you've got any add, subtracts in there, you've got to incorporate those factors as well. I'm sure I've got an example in here. We'll get to it. We generally report a measurement by recording all the certain digits plus how many uncertain digits. Just one. The very last one to the right is the uncertain. Four. I'm dehydrated. I'm taking Benadryl for this spider bite. And it's drying me out. Yeah. Yeah, pretty sure. And B was 23. Yeah. Now 24. You're asked to determine the perimeter of a cover of your textbook. Some of these work out better if you can draw a picture. So if you got a textbook, it's going to be something like this. And then the measurements are given to you there as the length is 39.36 centimeters. So it's the same on both sides. And then the width is 24.83 centimeters. Okay. So the question is, the perimeter of the textbook. So how far is it around? And then all they want is the number of significant figures. Right? This is an add problem. So you have to line up the decimal points. You got 24.83, actually twice. Right? Because it's down here too. You're going around, going here and here. And then you got 39.36, like that. So that's your add problem right there. Okay. So this is 6 is 18, carry to 1. You got 16, 17, 23. You got 8, 9, 10, and 28. 2, 4, 6, and 6 is 12. All right, I lined up my decimal points, and they all go out to the same uncertain value. So we can keep everything here. And the answer has 5 significant figures in it. Each one of these is only 4 significant figures, but the answer has 5. Right, because it expanded this direction by the addition. And we can keep that value. We can keep that decimal point. So our answer has 5.
So you don't want to round up and.
No. No. Now, if we staggered various ones here, then we would be limited to the farthest one to the left. And then we would round that. But in this case, the answer is E. You have 5 significant figures. Or 25. Consider the numbers 23.68 and 4.12. Okay. The sum of these numbers has some significant figures, and the product of the numbers has what? Okay. The product is easy, right? 3 and 4. The product is going to have 3 significant figures. Multiply them together. But add them, let me move this out of the way. Add them was the first one. It says, what's the sum of these? All right, so we got 10, 8, 7, 2. So the answer is going to be 4 by addition. And that means D, 4 and 3.
Now, how did you get the product?
Multiply them.
Just multiply the numbers.
Yeah, Product is multiplication.
Okay.
Quotient is division.
Well, would you even have to multiply them out?
No.
Because if you was to multiply the lowest one that has 3 significant.
Right.
figures.
The answer is going to have 3 with the multiply divide rule.
Oh, now to find.
And to answer this question, you don't have to do the math for the multiply. You do have to do it for the addition.
Yeah.
Because it doesn't follow the same rule.
Okay.
All right. 27. Using the rules of significant figures, calculate the following. 4.0021 minus 179. 179. Okay, bring that one down. That's 3, that's 2, that's 8, it's 3. So we have to round to this position. So that means it's 3.823, because 1 is less than 5. 3.823 is A.
What's this big one?
That's just to show me how far I can go to the right.
Because you have to stop where they match.
Yeah, I have to stop where this one is. That means this one brought down, but I have to use it to round this value here so that I stop there. 1's less than 5, so that one drops out and this one stays the same.
But the first one, that 4, okay, that's 5 significant figures in that number set.
Mm-hmm.
Okay, I get it.
Yep. $7.32. Now here's a complex calculation. I want to know the answer. 3.478 times 1.164 grams divided by 2.00 milliliters minus 0.169. 69 grams per milliliter. Okay. Remember order of operation. we do the parentheses first. Right, so if we multiply this one, and then there are no exponents, so then we do those, no multiplying because we've already done that. There's a divide, so we do these, and then this one. But these, this operation here uses the same rule, multiply divide rule. So you can do all three of these right here and settle on an answer there before you subtract that. Right. So I'm going to use a calculator for this one. 3.478. Oops. 1.164 times and then divided by 2. All right, so my calculator tells me 2.024196. This has three significant figures, 4 and 4. We're limited to 3 right here. So 4 is less than 5. This is 2.02. And then we're going to subtract 0.169. All right, let's brought that one down here. This is the product of these. And by the way, whatever you do to the number, you do to the units. So if this is grams, right, that's grams. This is a dimensionless number times that value, grams per milliliter. So this is grams per milliliter. That's grams per milliliter. So that confirms that we can add those together and subtract them because they're the same units. So let's see, I'm gonna do this with my hand. 9 from 1, 6 from 5. 1 from 9. Yep, 1 from 9 is 8. But I'm limited right here. So 1 is less than 5, 1.85 grams per milliliter should be the answer. C. Right. That's 32. Right. I'm gonna bleed over into lab time, I'm sure. Express this value in liters. 35. 781.2. 781.2 cubic centimeters. Okay. We want to convert that to liters. And about here, we have liters. All right, what do we know about cubic centimeters? 1 cubic centimeter is the same as 1 milliliter. So for clarity, we can put that in as a conversion factor. Right? So that leaves us with milliliters. And then we can convert milliliters to liters. There are 1,000 milliliters in a liter. So we got 781.2 times 10 to the minus 3 liters. Why can I do that? Because when I move this from the denominator to the numerator, it changes the sign. Okay. Then we need to resolve it. Let's see, the answer is in standard notation. So let's say this is going to move the decimal place to the left, 3 places. So we have 0.7812 liters. D. 37. It's becoming more and more complex. The pressure of the Earth's atmosphere at sea level is 14.7 pounds per square inch. Given that as our starting point, pounds per square inch. What is the pressure when expressed in grams per square meter? So we want grams per square meter. All right, what we're going to need here is a chain conversion. We're given conversion factors there, centimeters and inches. So we can do, when you have a complex unit of measure, you're converting, do one of them at a time. So I'm going to do inches first. We want to get rid of inches, and we know that we're given that the relationship of the standard system to the metric system is this value, 2.54 centimeters per inch. Right? And that doesn't get rid of inches though, right? Because that's linear and this is squared. So here's the trick. Once you've got the conversion for the linear, square the whole thing. And that squares this and squares that. Now that gets rid of inches. But when you do the calculations, don't forget to square this number, right? That's applied to everything inside the parentheses. Okay, now we have square centimeters. We want centimeters to meters. So let's see, centimeters, meters. There are 100 centimeters per meter. Centi means 100th. So it takes 100 of them to make a meter. We're going to square it again. That gives us squared here, squared there, and squared meters. So we got the meters taken care of. Now we need to do pounds. So what's our conversion? 2.205 pounds per kilogram. Right? So if I'm converting from pounds, English system to metric, I want pounds on the bottom. Because this is in the numerator, that has to be in the denominator. And pounds per kilogram would be 2.205 pounds per kilogram. So that gets rid of pounds. Now I can convert kilograms to grams. Grams needs to be on top. Kilograms on the bottom to cancel. What's the relationship? 1,000 grams per kilogram. So that's the thinking part. The rest is number crunching. So when we crunch numbers, I usually go that times that times that times that times that, then divided by this, divided by that, divided by that, divided by that, divided by that. Okay. So I have 14.7 and then times 1 times 10 squared. Squared is what? 10 to the 4th. 10,000. And then times 1,000. Okay, then I come back here and divide by 2.54 squared. So I got to square 2.54 first. Let's see. Then I can divide by it. And this one's squared, but that's 1. 2.205 divided into it. And my answer is, let's see, this is all multiply divide. So this is the only one that dictates the final answer. This is an exact number, exact number, exact number, exact number. Conversion factors are always exact. So the only one you have to consider in this problem is that one with 3 significant figures. So this is what my calculator tells me. Times 10 to the 7th. I can only keep 3. So 1, 2, 3. That's less than 5. 1.03 times 10 to the 7th. And then share. Okay, back. All right. Where was that? 37. Yes. Pick it up with 41. The density of liquid mercury is 13.6 grams per milliliter. What's the density of water? 1, roughly. All right, so this mercury is 13.6 times as dense as water. What's the density in units of pounds per square inch? Per cubic inch, excuse me. Pounds per cubic inch. 13.6 grams per milliliter. And we want to end up with pounds per cubic inch. We've already got, let's see, let's convert grams first. Are we given conversion factors? Yeah. We're given pounds and kilograms. So we need to convert grams to kilograms first. And then we can convert kilograms to pounds, which is 2.205 pounds per kilogram. That takes care of pounds. Now we need cubic inches. Well, we don't have a conversion from milliliters to cubic inches, but we do have one centimeters and inches. So what we want to do then is convert milliliters to cubic centimeters, right? That's 1 to 1. Now we can use a conversion from centimeters to inches. Centimeters, inches. 2.54 centimeters is 1 inch. And they both need to be cubed. That'll give us cube on the bottom. That'll give us cube here and take care of that cube. Right. So that's all the thinking we need to do. Rest is number crunching. So 13.6 times 2.205, 2.54 cubed. Enter. Let's have to figure this one out. Here it is. Times. And then divide by 1,000. Here. That's the only one, the rest are ones. So I get, let's see, are we in standard notation? No, we're in scientific notation. So 3 significant figures. I'm going to go ahead and round my answer. 4.91 times 10 to the minus 1 pound per cubic inch, which is B. With 6. Right. During a physics experiment, an electron is accelerated to 93% of the speed of light. What's the speed of the electron in miles per hour? Right, 93%. What is percent anyway? What does it mean? Percent simply means parts per 100 parts. We don't know what the parts are unless you're told in advance. Is it mass? Is it like 1 gram per 100 grams? Or is it 1 gram per 100 milliliters? Or is it 1 milliliter per 100 milliliters? But when you're told that a value is a certain percent of a given value, the easiest way to do that is say what percent actually means. 0.93 is the decimal equivalent of 93%. Because 93 parts per 100 parts is 0.93. Okay? So that's what we're going to do. We're going to take the speed of light is, I think they simplified it quite a bit, 3.00 times 10 to the 8th. 3.00 times 10 to the 8th meters per second. Excuse me. But we only need 93% of it, 0.93. Okay. Now we want to convert the units to miles per hour. All right. Let's take meters first. Convert meters to miles. We're given kilometers and miles. So let's convert this to kilometers. Meters, kilometers. Kilo means 1,000, right? So 1,000 meters in 1 kilometer. Okay. Now we can convert kilometers to miles. 0.6214. Miles per 1 kilometer. That takes care of kilometers. Now we got miles. Now we can work on the bottom, seconds. We want to convert time from seconds to hours. It doesn't give you, you have to know what it is. Yes. Yeah, 3,600 seconds in an hour. How do I know that? Because 60 seconds in a minute and 60 minutes in an hour. 60 times 60 is 3,600. Okay. So that takes care of seconds. So we check. We've got leftover miles, leftover hours. All we need to do now is crunch the numbers. So 0.93 times 3.8 and times 0.6214 and 3,600. And then divide by 1,000. Okay, I get. We can keep 3 significant figures. 6.24 times 10 to the 8th miles per hour. All right, he rounded off to 2. It was probably considering this 93%, but I consider that an exact number. I would go with this one. 6.24, but pick the best answer. Right out of that group, E is the best answer. All right. '49. In 1928, 29.3 grams of a new element was isolated from 660 kilograms of ore, molybdenite. The percent by mass of this element in the ore was. Okay, we didn't talk percent by mass, but when we say percent, often related percent mass, it just means mass. In this case, the mass of the element in grams per 100 grams of ore. So it's parts per 100 grams per 100. All right, so we have 29.3 grams of a new element is isolated from 660 kilograms. 29.3 grams of the element, whatever that is, in 660 kilograms of ore. This has to be in grams. Right? How do we get percent? You divide A by B times 100, correct? So this needs to be in grams. So we're going to convert kilograms of ore to grams of ore. At 1,000 grams for 1 kilogram of ore times 100 for percent. 29.3 and 660 and 1,000 and times 100. Oops, I messed up. Start over again. 29.3. And let's go ahead and multiply by 100. Now divide by 660 and divide by 1,000. There we go. So this is 3 significant, let's see, 660. All right, so this is going to limit it to 2 decimal places. 4.4 times 10 to the minus 3%. Oh, it's in standard notation. So if we take this one and move 3 places to the left, 1, 2, 3, 0.0044%. D. Okay. Let's see here. 50. We're going to convert temperatures. 409 Kelvin equals what? In Fahrenheit or Celsius? So let's do 50. If we've got 409 K, we've got to convert to Celsius first anyway. So let's convert to Celsius and see if it's either one of those two, D or E. Remember, so K equals C plus 273. That means C equals K minus 273. 409 and 273 minus that, 631. 136 degrees C. Yeah, there it is, D. So we didn't even have to go to Fahrenheit. We found our answer already. The 51 Fahrenheit scale. Melting point of a certain element is 391 C. What is it in Fahrenheit? All right, so if it's 3, let's see, wait a minute, 51. 391 degrees C. And what's our conversion formula? It's in useful information. F equals 9/5 C plus 32. Or your book may say 1.8. Same thing. Okay, so we got C, we just plug in C here. F equals 1.8 times 391 plus 32. And 32 is an exact number, so we don't have to worry about its effect on our calculation here. We've got 3 significant figures. 1.8, this is a conversion factor, so it doesn't influence. So 3 significant figures is what we're going to come out with. 391 and 32. So this is going to be 736 degrees Fahrenheit. D. Now, one of the tricks to doing these calculations is recognizing which ones actually influence the outcome in terms of significant figures. If you see this formula, then that value is exact and that value is exact. So they have no influence on the outcome. That's why I can keep 3 here. Let's see. 54. All right. I'm already into lab time. Let's see. There we go. 1984. This is one of those problems. They're giving you information you really don't need. In 1984, who cares when it happened, right? Some drums of uranium hexafluoride were lost in the English Channel, which is known for its cold water, about 17 degrees C. The melting point of uranium hexafluoride is 148 degrees Fahrenheit. What's the physical state? What we're looking for here is what temperature in terms of degrees C is this material. It's solid when it went in. Well, actually, it doesn't matter. We know that the melting point is 148. So if 17 degrees is not greater than 148, it's going to be solid. Right? So you can approach it two different ways. You can take 148 and convert it to degrees C and compare it to 17. Or you can take 17 and convert it to Fahrenheit and compare it to 148. Either way works. Let's take 148 and convert it to C. So 148 degrees Fahrenheit equals 9/5 C plus 32. Okay. That's 1.8. It's the formula for converting Fahrenheit to centigrade. Yes. I think the useful information, how is it expressed?
It's, CF equals 1.080.
1.8, okay. So I'm gonna have to start using this one, so don't throw you off. But 9/5 and 1.8 are exactly the same. Okay, so 148 minus 32 is, right? But on this side, it's a minus 611, and then divide by 1.8. Which is 64. Actually 64.4 degrees C. So the melting point of uranium hexafluoride is 64 degrees. The temperature is 17. Right? It's not hot enough to melt it. Right? So it's going to be solid. That's why the answer is A.
Can you set it when the possibility allowed you to certification?
Oh, because I moved this one to the other side. Yeah, I kind of skipped a step. Yeah, if I subtract 32 from both sides, I mean, that's allowable. So I subtracted 32 from there and 32 from here. That gives me this value. Then all I got left on this side is 1.8 times C. If I move that over here to the denominator, divide it into the what I got from this operation, and that gives me C. Let's see, who's next? God, we're not even into chapter 2 yet. Monolayer containing 3.23 times 10 to the minus 6 grams of oleic acid has an area of 20 cubic square centimeters. The density of oleic acid is 0.895. What's the thickness of the monolayer? In other words, the length of an oleic acid molecule. Okay, here's the experiment that they're conducting. 56. I've done this before. It's pretty neat. You take a still tray of water that's big enough, and you dust talcum powder on it. And then you take this oleic acid, which is a fatty acid. Yep. Have you taken A&P? No. Okay. Fatty acids have a hydrophilic side and a hydrophobic side. So oleic acid, I forget how many carbons it is long, but it has a hydrophobic tail. It doesn't like water. But it has an end over here that's like that. Right? Double bonded oxygen here and oxygen and hydrogen there. So this part is going to dissolve in the water. So we have water here. And let's make that like a head. Head there. And then the tail sticks up like that. Okay. That's what they're saying. So when you sprinkle talcum powder on your water, that's so you can see where, when you drop the oleic acid in there, how far it goes. And you'll see it. When you drop it in there, it goes like that. Makes hopefully a circle. Well, the circle is composed of these guys right here. And the thickness there is the length of that molecule. Okay. Now, it's all based upon the geometry of a cylinder. Right? Cylinders, we usually think of cylinders as like long this way and small circle, propagated that distance. But it doesn't have to be. It can be a thin cylinder this big and only that thick. So we've got a cylinder here with this thickness right here, that height, times this area. That's the volume. All right, so if we know the density of oleic acid, 0.895 grams per milliliter equals its density, that's equal to mass divided by volume. And the mass is 3.23 times 10 to the minus 6 grams. I think that's right. Yep. And they well, they calculate the area for us. All right. So this is 20.0 square centimeters. So our unknown is what's the height. We can calculate the volume for this one because we have that mass, volume unknown, and we have the density. So we can calculate the volume. Right? So the volume, if we do a little footwork here, move the volume over here, move this value over there, 3.23 times 10 to the 6th, divided by 0.895 grams per milliliter, then the grams cancel, leave us with milliliters. Okay, so the volume of that cylinder in milliliters is 3.23 6 minus 6, excuse me. I better start with 3.23. Divided by 0.895 gives us 3.609 times 10 to the minus 6 milliliters, which is the same as cubic centimeters. So the volume of this cylinder is area times height. Right? Remember that from geometry. We know what the area is. We know what the volume is. 3.609 times 10 to the minus 6th cubic centimeters equals an area of 20.0 square centimeters times height. So height's going to be this number divided by that number, which is 1.804 times 10 to the minus 7th centimeters. And the answers are given in centimeters. Okay, how many significant figures can we keep? Well, let's see, we've got 3 here. Got 3 there. So I'm going to have to round it down. 1.80 times 10 to the minus 7. That's why the answer is D. That is the thickness, the length of that molecule is 1.80 times 10 to the minus 7 centimeters. Okay. All right, 57. The density of gasoline is 0.7025 grams per milliliter. Density of gas at 20 degrees. When gasoline is added to water, what happens? Well, I'm sorry, it floats. Yeah. Well, it doesn't mix with water either. So it's less dense than water. Water is 1. So anything less than 1 is going to float. Anything greater than 1 is going to sink. So it'll float on the top. Okay. $58. A piece of zinc with a mass of 12.14 grams is submerged in 46.3 cubic centimeters of water in a graduated cylinder. All right, so let's draw a picture. Graduated cylinder. Okay. 46.3. Let's say it's a 50. So we have a 46.3 cubic centimeters, which is a milliliter. And then we submerge 12.14 grams of zinc. All right, there's our zinc. So when we drop that in there, what's going to happen to the water level? It's going to go up somewhere. Okay. All right, what else? Other information do we have? 12.14 grams of zinc. Okay. The water increases to 48 cubic centimeters. So this is 48.0 cubic centimeters. What's the density? We'll go back to our definition. Density equals mass divided by volume. So the mass, we got that. 12.14 grams. What's the volume? It's the difference between these two. 1.7 cubic centimeters. All right. Notice we can only have 2 significant figures in this operation. Let's see, 12.14 and 1.7. So I get 7.141176 grams per cubic centimeter. If we only have 2, that means 7.1 grams per cubic centimeter. There's B. This one's kind of tricky, right? Because it's got an answer, 7.141. Right? If you don't round it to the correct number of significant figures, then you put the wrong answer. Okay. And next. 62. The boiling of water is A. What are our choices? Well, there's no none of the above or 2 of the above or all that garbage. So once we find the right answer, we can stop. Boiling of water is a physical change. Is that true? Yeah, it's a phase change. But we're given a reason, because the water merely disappears. That would be you cannot create or destroy matter. Right? So A is false on its face. Physical change, B, because the gaseous water is chemically the same as the liquid water. That is true. And C, D, and E are all chemical changes, and it's not that. It's not a combination either. It's just simply a physical change, because the vapor is the same identity as the liquid. So 62B is your answer. All right, I put this one in here to give you a taste of what standardized exams in chemistry would look like. They're always giving you these kind of strange problems. What we have here is A through E, and the first one you got, it looks like you've got actually 3 types of atoms. We're assuming that each circle or each square is an individual element, individual atom. And what you've got in A, they're so far apart, what you have is there is a mixture of gases. That's a solution. A homogeneous mixture of gases is A. B is a regular arrangement, very structured. That's a solid of a single element. C is a compound, but it's pure, right? It's got one element bound to another element, and they're far apart, so it has to be a gas. Then D is 2 types of elements mixed together, so that's a mixture, but they're not homogeneous. And they're more than likely, well, we don't know exactly if they're solid or liquid, but they're definitely heterogeneous mixture. And then E is a regular arrangement of elements and compounds. So let's see if we can answer the question. Which best represents a homogeneous mixture of an element and a compound? Well, that's E. I just talked about that one. Right? All the squares are elements. The circles, open and filled, are different elements, but they're bound together in a compound. So that's a homogeneous mixture, and you can see their regular arrangement. Which best represents a gaseous compound? Let's go back up. C, yeah. C is a gaseous compound. I'm not putting these on the board, so you have to pay attention. Let's see, we have another one, 72. Which best represents a solid element? Probably B, right? That's definitely an element. And it's regularly arranged. It's got to be a solid. 73. Which best represents a heterogeneous mixture of 2 elements? Heterogeneous D, yeah. Those are individual elements, but they're not uniformly distributed. Okay. And let's look at 75. This one's in there to emphasize the difference between mass and weight. Which one of these has a different value on the moon compared to Earth? Mass is going to be exactly the same. Time doesn't change. Numbers, moles is numbers of things. That doesn't change. Weight will change. So B is the answer to 75. 80. Which separation technique is based on the difference in the volatility of the substance to be separated? Volatility. What that means is the more volatile the substance, the more likely it is to change from liquid to gas at a given temperature. So you got 2 substances here. If this one's more volatile than that one, the forces driving this one into the gas phase are much stronger than they are for this one. So we use that information to separate mixtures of, well, think moonshine, right? If the mash is actually water and methanol and ethanol and some other things. So the most volatile component of that is methanol. Right? It's going to come off first. That's what you catch and throw away, because you don't want to kill your customers. That's wood alcohol. You don't drink. Make you go blind first and then it'll kill you. Distillation is the process where we heat the substance up, we heat the mixture up, and the more volatile one comes off first. That's methanol. Then after it's all gone, ethanol comes off. And then after it's almost all gone, ethanol and water come off. So distillation is the physical separation of components in a mixture based upon their volatility. You could also say it's based upon their boiling points too. Both ways work. But the answer is B, distillation. We separate filtration on particle size. Right? Bigger particles are held by your filter. The rest of it goes through. Solvent extraction, well, that's something that's differential solubility in two immiscible liquids. We don't have time to talk about that. Paper chromatography is the affinity of a compound or an element for the paper as the solvent moves up through it. You spot it on your paper, spot the mixture on your paper. Let's just draw an imaginary line there. So you make a spot of your mixture here, and then you put it in a container and close the lid, and you have just enough. We call this the mobile phase. Right, this is the stationary phase, the paper, and the mobile phase is the liquid. Let's just say, for argument's sake, it's ethanol. That's my abbreviation for ethanol. And it starts moving its way up, right? Moving its way up. Once it encounters those spots, it dissolves them, all the components, and then there's a differential attraction between the stationary phase and the mobile phase. The ones that like the mobile phase most will move the fastest because they stay in the mobile phase longer. So they'll move up and they'll be up here. And then the ones that prefer the paper to the mobile phase, they'll be down here. And so a differential attraction to the stationary phase versus the mobile phase is the physical characteristic that paper chromatography is based on. All chromatography is based on. There's a whole host of chromatographies. All right, we finally got to chapter 2. We have a little bit of time left so we can talk about our lab. All right, we're going to do some graphing. Everybody got a copy of the graphing lab with you? Didn't I hand that out already? Maybe I didn't hand it out. Okay. Check for just a second. There it is. Huh? You think you might have it? Yeah,
You didn't hand it out.
that's why I've only got 3 left, because some of you already picked them up. Okay, chapter 2 now. And we'll go on. The first people to attempt to explain why chemical changes occur were the ancient Greeks. Yep. That's E. 2. The first chemist to perform truly quantitative experiments was Robert Boyle. So that's B. 3. The scientist who discovered the law of conservation of mass is also called the father of modern chemistry. He was the Frenchman who got his head cut off in the French Revolution. Lavoisier. E. He was also a tax collector. He wasn't murdered on the guillotine because of his scientific endeavors. He was murdered because he was a tax collector. Which of the following pairs of compounds can be used to illustrate the law of multiple proportions? All right, if we're going to have multiple proportions, that's 4. We have to have an element, 2 different elements And you have to be able to say, all right, if we hold one of them constant and let the other one vary, they vary by whole number increments. So we look at our choices and say which ones have the two components, right? Ammonium and ammonium chloride don't fit, right? Because you've got NH4 in one and NH4Cl in the other one. That doesn't work. You got to have the same on both sides. Zinc oxide and zinc chloride, nope, wrong again. Water and HCl, wrong again. NO and NO2. NO2. Now, if we hold this one at unity, then these vary by, this one's double what that one is. That's multiple proportions. So D's the answer for 4. All right. There we go. Okay, 7. Let's make some room. I need a little bit of logic here. Plus, one of the laws. A sample of chemical X is found to contain 5 grams of oxygen, 5 grams of oxygen, 10 grams of carbon, and 20 grams of nitrogen. Okay. The law of definite proportions would predict that a 70-gram sample should contain how much carbon? So how many grams is this? 20, 30, 35, right? So the law of definite proportions tells you that the ratio by mass of all the elements in a compound is fixed, no matter how much of it you have. So if we go from 35 grams to 70 grams, what have we done? We've doubled it, right? That means each one of these has to be doubled. You can prove it to yourself. That would be 10 here, 20 here, and 40 there, right? 40, 60, 70. So we're good. Now, to answer the question, we're looking for carbon. 20 grams of carbon, right? E. All right, number 9. Which of the following statements from Dalton's atomic theory is no longer true according to the modern atomic theory? A, elements are made up of tiny particles called atoms. Is that still true? Yep. How about B, atoms are not created or destroyed in chemical reactions? Yep, that's still true. All atoms of a given element are identical. Nope, sorry. Isotopes. And then all the statements are true. We found a false one, so E can't be it, and D, atoms are indivisible in chemical reactions. That's true also. So C is the answer. We found our answer. 11. The chemist credited for inventing a set of symbols for writing elements and a system for writing the formulas of compounds and for discovering selenium, silicon, thorium is. Now, I didn't cover all of those about this one person, but it should be in your textbook. The person that gifted us with our symbolic language for the periodic table now is a Swedish chemist called Berzelius, D. Avogadro's hypothesis. Remember what Avogadro said? The illustration I gave you was 2 containers of gas, right? If their volumes are the same, the internal pressures are the same, and the temperatures are the same, then the number of particles in each one must be the same. Let's see, which one of these statements satisfies that? Let's see. How about D? At the same temperature and pressure, equal volumes of different gases contain an equal number of particles. Same temperature and pressure, equal volumes. Yep, that meets all the conditions. That's a statement of Avogadro's hypothesis. Now, he didn't popularize it. That remained for one of his students. His name was Cannizzaro. He was the one that actually promoted the hypothesis and solved massive problems in the late 19th century in Europe primarily. They were running into difficulty with their chemical reactions. I don't think I had time to discuss that in detail. But it was costing people their careers if they were in university and costing them money if they were chemists for a company. So Cannizzaro saved their bacon, so to speak. 13. The first scientist to show that atoms emit any negative particles was, remember the cathode ray experiment? J.J. Thomson. Yeah. Thomson was the one who proved that negative particles were being emitted by atoms. Right. And he also determined the charge to mass ratio of the electron. He didn't determine the mass of the electron. He didn't have the technology at that time. Okay, 14. Many classic experiments have given us indirect evidence of the nature of the atom. Which of the experiments listed below did not give the result described? Okay, E says all of the above experiments gave the results described. So all we have to do is find the one. The Rutherford experiment proved the Thomas plum pudding model of the atom to be essentially correct. What was the plum pudding model? Plum pudding model says that the atom is like this, and you have these electrons here floating in a sea. These are the plums, and the pudding was positive charge, not individual particles, just the pudding is a positive charge, and the electrons were these particles coming out. Right? So what did Rutherford's experiment do? Remember the gold foil experiment? He fired alpha particles at gold foil, and instead of going straight through, which they would have here, because there's really nothing to stop them, going straight through in a line, they ended up going like all different directions. Rutherford's model was the nuclear atom. He said that the nucleus was where most of the mass was located, and it had protons. When he conducted the experiment, that's all he knew about. He said the protons are actually particles, but they're very massive compared to the electron. And the electrons were out here. So most of the alpha particles just went straight through. But occasionally they glance off like that, or they bounce straight back like that. That means that A is false. Rutherford's experiment did not confirm the plum pudding model. It buried it. The plum pudding model was dead once Rutherford published his work. And many authors attribute the plum pudding model to Lord Kelvin. I don't know if that's true or not. He was the one that gave us the Kelvin temperature scale. 15. All right. The scientist whose alpha particle scattering experiment led him to conclude that the nucleus of an atom contains a dense center of positive charge. Right. We just talked about him, Rutherford. Let's see. 16. Alpha particles beamed at thin metal foil made what? Well, let's see. Pass directly through without changing direction? Yeah, they can do that. Be slightly diverted by attraction to electrons? Yeah, that's possible. Be reflected by direct contact with the nucleus? Yeah, all three of those. So E is the answer, A, B, and C. 17. Which of Which one of the following statements about atomic structure is false? Okay, A, an atom is mostly empty space. Is that true? Yeah, most of it is. Almost all the mass of the atom is concentrated in the nucleus. That's also true. C, the protons and neutrons in the nucleus are very tightly packed. Oh, yeah. In fact, what happens when you get positive or like charges pushed close together? They repel each other, don't they? They want to fly off. How do we keep them in the nucleus? That's the function of the neutrons. The neutrons are there to stabilize the nucleus. So there's something going on in there, and I'm not competent to describe what it is, but the neutrons are there to stabilize the nucleus and keep those positive charges together. Let's see. D, the number of protons and neutrons is always the same in the neutral atom. No. You can have different numbers of neutrons. You have the same number of protons in different atoms of the same element, but you may have different neutrons, which means isotopes. So D is the false one. 20. Okay, remember when we wrote the symbol? Let's see, 20. We had reserved places for the information. Let's see, A is 6 and 14. 6 and 14. All right, so what does that mean? That means this is the Z number, and it's equal to 6 protons. This is the A number, and it's equal to 6 protons plus 8 neutrons. Right? This mass number is the sum of protons and neutrons. So if you know this number, subtracted from that number gives you the number of neutrons. Okay. So which of these is incorrect? Well, let's see. We have to look at, let's look at the Z number first for each one. Right? Carbon. Look at carbon. There's your Z number. That's the number of protons. It's good. As far as that goes, we're not looking at the mass number yet. We're going to see if we can differentiate, get the false one from the Z number first. 17 for chlorine. Yep, that's true. Phosphorus, 15. Yep. 19 for potassium. It's over here. There's 19. Okay, well, good. And the last one, 8 for nitrogen. No, 8's oxygen. So that E is false. It's got one too many protons. Right. So we didn't even have to look at the mass number. We found the false one just by looking at the number of protons.
You do show, say all those Z numbers was right. Then what would we do? To find the incorrect.
Then you go to the mass number. And it's kind of jumping ahead, but the mass numbers are buried in these values here. These are fractional values. The reason for that is that you have a certain number of isotopes with a given number of neutrons, which gives you a mass number of something. And then you have other isotopes with a different number, and depending on their abundance, they will shift this value, which is never a whole number. Now, a mass number is always a whole number because it's protons plus neutrons. But this is atomic mass, which is a weighted average of all the isotopes. That's why it's fractional. But it can give you a clue. Say carbon C14 there. Is that true? Well, see, carbon. Well, most of them are 12. But we do know, you have to know something about the isotopes. Carbon-14 is radioactive, right? That's what you use for dating things that are less than about 10,000 years old. So in this case, I wouldn't give you a problem where you would have to go to that number. Not at this stage. Okay. All right, how about 21? The element rhenium, Re. Now, that's one that you didn't have to memorize, but it's right over here. Exists as 2 stable isotopes and 18 unstable isotopes. Rhenium-185 has in its nucleus what? Rhenium. You can always find out how many protons it has. All you have to do is look at the periodic table. 75 protons. Okay. Rhenium-185 is one of those isotopes. So 185 goes right here. So we can say 75 protons and then 110 neutrons, right? 110 plus 75 is 185. So let's see, D would be the answer. 75 protons, 110 neutrons.
And you can minus the 75 and the 185 to get the 1.
Yes.
Okay, I just want to make sure.
Yeah, that's how you do it. Okay. 22. Which among the following represents a set of isotopes? Atomic nuclei containing. All right. So in order to have isotopes, the pair or the triplet or however many have to have the same number of protons to be the same element. If they're not the same element, they can't be isotopes of each other. So if we look at 1, it has 20 protons. Which other one has 20 protons? 4. 4 has 20 protons. So those are isotopes of one another. 2 and 5 are 21 protons. Okay, and that leaves 18 protons with 3, and nobody else has that many protons. So 3 is left out. So 1 and 4 and 2 and 5. 1 and 4, 2 and 5. D.
You said it has to have the same number of protons to be a isotope, right?
Yes.
Okay.
They have to be the same element, and that means the same protons. If you change the protons, you got a different element. So that would be D. I already said that, didn't I? Okay. How about this one? 28. A species with 12 protons and 10 electrons is. Okay, we got 12 protons, but 10 electrons. All right. If you got 12 positive charges and only 10 negative charges, what's the charge on the atom? You got 2 extra positives, don't you? So it's an ion. Let's see. Oh, so they want us to tell them what the element is. All right, 12 protons would be magnesium. And it has a 2+ charge. All right. The only way that you can get a charge on an atom to make an ion is change the number of electrons. You can't change the protons or you get a different element. So it's add or subtract electrons. In this case, we subtracted 2 electrons, gave us an excess of 2 positives. That's why the charge on that ion is 2+. And the reason it's magnesium is because 12 protons says it has to be. There's no other option. So that would be C. All right, 29. Let's see, 1939, 1939, K plus. All right. So they want to know protons, neutrons, electrons. Protons, neutrons, electrons. Protons is easy, 19. Neutrons is easy, 20, right? How many electrons? Well, if you've got a +1 charge, we have to have a deficit of 1 negative. So this has to be 18 electrons. So 19, 20, and 18 is E.
So if you minus an electron, it makes it a positive.
Uh-huh.
If you add an electron, it makes it a negative.
Yes. If you're starting from a neutral.
Yeah.
Yeah. Right. See, I can get it.
How did you get that? Electrons, one, last one.
What did I say? 19 protons?
19.
Because if it's a positive.
Yeah, because what was it, potassium? Potassium had a +1 charge. It has to be an excess of 1 proton in order to give you that 1 plus. Right, you're deficient in 1 negative. I think of it as a neutralizing situation. If you have 19 positives and 19 negatives, that's 0, right? Neutral. But if you have 18, now you've got an excess of 1 positive. Right, 33. Which of the following are incorrectly paired? Right, what we're looking at here is names of groups and regions. So if we say SR, we know SR is strontium. So where's strontium located? It's right over here. It's an alkaline earth, right? That's true. That's good. Alkaline earth. TA is tantalum. I don't think I had you memorize it, but you can find out where it is right here. It's a transition metal. Right? All these are transition metals. So that's true. Tantalum's there. F. Right here. These are all halogens. That's correct. H is hydrogen. Hydrogen's over there. It's not a noble gas. Right, so we found our bad one. And ruthenium is also a transition metal. Here. So our bad one was D, H. Hydrogen is not a noble gas. Okay, which of the following are incorrectly paired, right? In this case, you just have to know your symbols, right? Is phosphorus that? No. PR is down here somewhere. Promethium. I think that's promethium. This is protactinium. I always get those confused because I don't use them very much. So we found our wrong one. Phosphorus is P, not PR. And 35. Let's see. Which of the following are incorrectly paired? Okay. Is copper Cu? Yep, that's cuprum. Carbon is C. Cobalt, CO. Okay, yep. Calcium, Ca. Cesium. No. Cesium is Cs. Ce is cerium. Cerium, let me see, where is cerium? Here it is. Cerium. It's a lanthanide. All right, so there's the wrong one. E is the wrong one for that. 36. Let's see. Antimony is Sb. Yeah, that's Latin for stillbium. Silicon, Si. Yep. Silver, argentum, Ag. Argon, Ar. Yep. Aspartame, As.
Isn't it supposed to be 18?
Yeah. As is arsenic. Right? AS is arsenic. Astatine is AT. Did I have you memorize that one? Okay.
It just kind of be, this element, is it like a quiz or a test at a time?
No,
Or is
it's
it
going to be
just-
buried in this test, yeah. With these questions, these types of questions. But if you don't know them, it's going to come back to haunt you. Because you can't write formulas of compounds, you can't write chemical reactions unless you know your symbols. They have period.
I wrote that card to you, not just each other.
Oh, are they in a class somewhere too?
No.
They just interested.
No, they're just made to help me.
Oh, that's good. You've got a,
I work in a lab.
okay,
They know some of this.
okay. What kind of lab is it? Oh, it's a med tech lab? Okay. I thought you looked familiar. Occasionally, we see Dr. El Haraki for my wife's lupus anticoagulant. He's got her on blood thinners. Yep. Is he feeling any better? He had back trouble, I think.
I don't think much of the
Yeah.
doctors. I mean, more than nurse practitioner said the main
Oh,
doctors.
okay.
They're only there a week at a time. They switch out and go to the hospital for a week.
Yeah.
Okay.
Yeah, he was kind of cut back on his rounds, I think, because his back was bothering him. 37. We do that one already? No, we haven't done. All the following are characteristic of metals except, are they good conductors of heat? Yep. Malleable. Yep, that means you can shape them. Ductile means you can stretch them into a thin wire. Often lustrous. Yeah, if they're polished, they are. Tend to gain electrons in chemical reactions. Now, metals tend to lose electrons. So if you look at your periodic table and look at these charges, you're going to find that they're all positives for these metals. You only get into negatives when you're over in the non-metals. All right. Let's see, 41. Now we're going to solve a problem. You're given a compound with a formula MCl2. 1 MCl2. That's chlorine. This is a placeholder for a metal. Right. All right, so this is either a type 1. Actually, we don't know if it's a type 1 or a type 2 because we don't know what the metal is. But they're going to give us some more information. You're told that the metal ion has 26 electrons. 26 electrons in that metal. What's the identity of the metal? Well, if chlorine is a halogen, it's a -1 charge. So it's 2 minuses total for those two, right? And that one metal has to balance that 2 minus to be a neutral compound. So the charge on this metal has to be a 2+, correct? You with me so far? How did I get to that? Okay. So if this metal has a 2+ charge and it's got 26 electrons, that means it has 2 protons extra. It'd be 28 protons. Now we can find out what it is. Nickel. There you go. E. There's a certain degree of satisfaction to solving problems. Let's see, 45. How many oxygen atoms are there in one formula unit of calcium phosphate? Calcium phosphate. There. So how many oxygen atoms? We got 4 in that polyatomic ion, but there are 2 of them. So we should have 8 oxygens.
Can you repeat that?
Assuming this formula is written correctly, you have 3 calciums, you have a parentheses around this polyatomic ion, phosphate.
Mhm.
with a parentheses and a subscript of 2, that means there are 2 phosphates actually there.
Okay.
So that means you have 4 plus 4, or 2 times 4 is 8.
Okay,
8 oxygens. That would be D. Now we're going to name some compounds. 47. What's the correct name for this one? FeO. First of all, is it a type 1, type 2, or type 3? We can eliminate type 3 because there's a metal, right? Type 3 is only metal, non-metal, non-metal. So it's either a 1 or a 2. Then you look at the metal and say, is it a fixed charge, or can it be different charges in different compounds? And iron can be different charges, right? Because it comes from here. Transition metals, with the exception of these 3. Or it's the other ways, like that. These 3. So to name it, we just say iron oxide, and then we put the charge, right? Oxygens are -2s. How do I know? When combined with a metal, they form ions. So these are zeros, these are -1, these are -2. So oxygen is a -2. You have to know what it is. If you don't know that that's -2, then you're stuck. There's no way to figure the rest out. That means this one iron has to be a 2+. Okay, so iron 2 oxide is the name of that compound. And that would be B. 48. The correct name for Ca2+. This is a trick question. Can calcium have more than one charge? Where does it come from? Alkaline earth. They're all 2+. When they have a charge, they're always 2+. So we don't want to be redundant. Right? That's one of the rules. Unambiguous and non-redundant. So this is calcium ion. And we know it's a 2+ because of where it comes from in the table. We don't have to say what the charge is, because it can only be that charge. So calcium ion is the correct name for that. A calcium 2 ion is redundant. That's why B is false. C is the correct answer. Let's see, let's scroll a little bit, let's see what else we can find. 51. What's the subscript of barium in the formula of barium sulfate? Barium sulfate. Okay. Is that an element? No, there's no sulfate in the periodic table. That's a polyatomic ion. So you've got the table there. You can look up sulfate. If you don't have it memorized, look up sulfate and you'll find that it's SO4 2-. Barium comes from the alkaline earths, so it's a +2. Okay. Barium 2+. You only need one of each. A 2+ neutralizes a 2-. So BaSO4, the subscript of barium is 1. Right? If you've got one symbol there, then the subscript has to be 1, otherwise it won't be there. We don't write 1 in there, because that's redundant. Are we okay? All right. 53. The formula for sodium dihydrogen phosphate. So we've got sodium dihydrogen phosphate. That's a big name for a polyatomic ion. Dihydrogen phosphate. You look it up in your polyatomic ion list, you'll find it has a -1 charge. Sodium has a +1 charge. That's it. Sodium NaH2PO4. But this acts as a single unit. There's a minus charge over that entire unit. So the answer is A. And you don't have to write the charges in when you write the name. I just do that so I can figure it out. All right. 56. All the following are in aqueous solution. What is incorrectly named? Right? If these are in aqueous solution and they start with a hydrogen, it's safe to assume that they're acids. Right? So are they named correctly? H2SO4. You start with, if it's got oxygen, you don't start with hydro. So we have to look to this polyatomic ion. This is sulfate, and H's become X. So we say sulfuric acid. That's correct. H2CO3. Right? Oxygen again. So this is the carbonate polyatomic ion. So H becomes X. This is carbonic acid. That's what you drink when you drink pop. You're drinking carbonic acid. Don't worry, it's a weak acid. It's there for the fizz. Phosphoric acid, is that correct? H3PO4. This is phosphate. Polyatomic ion. H become X, so this is phosphoric acid. Okay. HCN. Okay. There's no oxygen there, so we started with hydro. This is the cyanide ion. So we say hydro. I becomes it. Hydrocyanic acid. All right, so that one's wrong. And the last one, hydrochloric acid, is correct. So the wrong one is D. It's not cyanic acid, it's hydrocyanic acid. Right. Coming up on 3 o'clock. How much more time? 50. Okay. I gotta have enough time to lead you into graphing techniques, and then you can take it home and finish it at your leisure. 59. Which of the following names is incorrect? Are correct? Sulfide. Is that correct? S2-. Yeah, that's sulfide. Ammonium chloride, NH4Cl. That's correct. Acetic acid, HC2H3O2. Yep. It's acetate, and H become X, so acetic acid. Barium oxide. They're all correct. All of them. All right. Complete this table. All right, we've got 1, 2, 3, 4, 5 down. That. Okay, 1, 2, 3, 4, 5 across. Okay. So we've got a symbol. We've got number of protons, number of neutrons, number of electrons, and net charge. Okay. So we're given this one. And we're given, let's see, this one. Let's see, we're given this one, and we're given this one, this one, and we're given this one, and given this one, and we're given, let's see, this one. I think that's right. Okay, so let me change color for the missing ones. All right, if we've got PB 206, the only way to find the number of protons is look it up. Lead, 82. So the number of neutrons is going to be 124, right? 124 and 82 is 206. The number of electrons, it's neutral. So the number of electrons will be equal to the number of protons. Okay? And the net charge is 0. Right? There's no charge on that. How about this one? 31. All right, we'll have to find that one. 31 is gallium. Okay. But it's got a charge. 3 plus. That means it's got 3 more protons than electrons. It means the number of electrons is 28. Now, you don't have to, but you can put the mass number up there. 52 protons. That's tellurium. Right? 52 protons, 54 electrons mean 2 extra negatives. That means the charge is 2 minus. Okay. And manganese, the number of protons for manganese is 25. And it has a 2 plus charge. So that means we have 2 fewer electrons, 23. Okay, so that's how we fill that chart out. I'm going to leave this one for you guys. You can figure that one out. We use the same methods. And this is to test your memory. Right? Silver is Ag, calcium Ca, iodine is I, copper Cu, and phosphorus is P. And then your compound. Right? You look at the formula and say, is it a 1, 2, or a 3 type? If it's got a metal in it, it's either a 1 or a 2. Then you look at the metal. Is it a fixed charge or a variable charge? If it's a variable charge, then you got a type 2 compound, and you work it from there. And be aware of these polyatomic ions. That's acetate. And hydroxyl is a polyatomic with a -1 charge. Carbonate has a 2 minus charge. Right, so you can work those from there. Let's see. Here we're writing the formulas from the names. Nitrate ion, that's not right. Nitrate is, let me erase this. It gets in the way. Uh, 65. Nitrate is NO3 minus. So I think something's messed up with that one. That's not right. Can't see it anyway. Aluminum oxide, that's correct. Ammonium ion, that's the only positive polyatomic ion in that chart is ammonium. Perchloric acid, copper 2 bromide, you can do those. ClO4 is perchlorate ion. So that's why it's perchloric acid. Name the following compounds. Right. Aluminum is always a 3 plus. So we don't have to say what the charge is. Ammonium nitrate, those are fixed charges. NaH, this is one that we didn't spend a lot of time on, but when a metal is combined with hydrogen, the hydrogen becomes hydride. And if you're looking for a charge, the sodium dictates the positive. And the hydrogen, in this case, is a -1. Most of the time, hydrogen is a +1 if it comes first. But if it comes second with a metal, it's a -1. That's sodium hydride. And this is potassium dichromate, carbon tetrachloride. That's a type 3 compound. Now, it's carbon and chlorine. They're both nonmetals. So in that case, you just use the Greek prefixes and say how many there are. There's 1 carbon, so we don't say mono for the first one. Tetra is 4 chlorides. Silver chloride. Silver can only have 1 charge, even though it's a transition metal. Silver is a +1 charge always. So we just say silver chloride, and that's good. Calcium sulfate, let's see, nitrous acid. NO2 is nitrite. Ites become us's. Ates become X. Ites become us's in naming an acid. Dinitrogen trioxide, there's a nonmetal type 3. And tin iodide. Tin can have usually 2 charges possible, either a 2 or a 4. So you have to say what it is. It's not a transition metal. It's not over here. It's over here. And many of these have variable charges. Right. So that's why your periodic table has these different charges in the upper right-hand corner of the little boxes. Now, when you look at the nonmetals and you see all these different charges here, those are actually not charges, but oxidation states, and we haven't talked about that yet. So if you're looking for a charge, look at the first one in the group. Fluorine is always -1. Chlorine, the first one is -1. Bromine -1. Iodine -1. That's what they will be in combination with a metal. If you combine them with a nonmetal, then I have to show you later how to calculate that oxidation state. So don't worry about that. Just these are always -1 combined with a metal. -1, -2, -3, +3, +2, +1. And then you've got these, I think it was that one, silver, copper, zinc. Yeah. No, silver, cadmium, zinc, excuse me. Silver's 1, cadmium is +2, and zinc is +2. So it goes like this. +1, +2, +2. Those are fixed charges. The rest of them are variable. There's some more. Write the formulas from these names. You just need practice. I would note that if you need more than 1 polyatomic, you have to use a parentheses. If you don't use a parentheses, then you're splitting up polyatomic, and you can't do that. Polyatomics have a fixed charge distributed over the entire unit. All the atoms in the compound are in the ion. So don't forget to use a parentheses. These are 2 ways of writing acetic acid. Your book probably uses this one, HC2H3O2. This one is another way of writing it, which gives you a little more structural information, but you don't have to know that one. Okay. All right. $50, or less than 50 minutes. Okay, I'm gonna have to skip that one. Just write down the answer is D for this one. And B for 87. E for 88. A for 90. D for 91. 94 is C. Some of these are repetitive. We've done these types before. 95 is A. And that's it.